All right. Thank you so much for inviting me. My training is in cognitive systems and artificial aid in AI in general. And I've always been inspired by the HRI community, and I always wanted it to adopt me. So I'm super glad that you invited me here. I'm very grateful for it. It seems like you all have adopted me, and hopefully I have some very interesting things to share with you. All right, so this is a community where I never need to defend the problem. Like, we need robots, we need humans to be able to program those robots, because we don't know the whole the whole space of deployment use cases that the robots would be used in. So one way to approach this challenge is to design robots that can be trained by humans, right, in natural communication modalities. And this problem is what's called the interactive task learning. And this problem sort of came out of this workshop, this forum that we had back in 2017, where people from variety of different backgrounds, from machine learning, cognitive architectures, robotics, psychology, computational linguistics, came together and started discussing what are the challenges that this problem poses, right? So the problem is this: like, you don't have any knowledge. The robot doesn't have any prior knowledge about a task. So how do you teach what to look for? How do you teach it what goals it should be following? How should it be structuring tasks? So it's starting just from zero knowledge, blank slate, and how do you build up that knowledge in a robot? And it's fairly cool. It's super interesting from a variety of different perspectives, right? So, like a honest computer cognitive scientist, when I start a problem, and there's a problem here, no video. Let me see if this would help. All right.
Put it on your head. Ooh, good try. Try again. On your head, on your head. Put it on your head. Go ahead. Ooh, good try again. Good try, but you're missing your head. You gotta put it here on your head. Do you wanna try again? You need help? Help? Okay, I can help.
All right, so that's the best interactive task learner that I know. And this is how I usually start any problem. And then I think any cognitive scientist and cognitive systems person would tell you that first time they're posed a problem, they go looking for the human who would do that problem and then start studying them, right? So there's some very interesting things that, Ishan does when he's trying to learn, right? So first thing to notice is that there's a human teacher there who's trying to make the teaching task, the learning task easier. There's a lot of back and forth, right? So there's no training phase, testing phase, anything like that, right? It's all continuous, it's all experiential. As Ishan does the task, he's getting feedback about how to do it better. And I think what's most interesting is that he can recognize his own failure. He can just ask for help when he knows he can't do the task, right? So that framework is what we are trying to build towards. We want to build robots or agents that can actually take into account the entire space of information that's present in human instruction. So I've been working on this problem for over a decade now. So this started when I was back in grad school, and then it just went on going. So I went to University of Michigan and with Johnny Laird, and so he's continuing to work on the problem, and then I'm also. So we are all both together working on them. There have been several, insights that we have found as we are building these systems that are learning like humans do, that are trying to leverage the structure in human teaching. And most recently, Rosie, which is an interactive task learner at University of Michigan, won the best demonstration award at AAAI. Right, so fairly cool work. I would encourage all of you to go and find. Look up some of the papers there. All right, so in this talk about two questions. The first is, how would humans like to teach tasks? Because unless you understand how humans actually teach, it's very hard to design robots that are able to leverage the full structure that's apparent in human teaching. And so thank you, Matt, for asking questions. Found some answers for you. So uh, feel free to ask me any questions about what she found, and I'll share some of the summary findings here. But she structured a cool study that helped us unpack human teaching. And then the second parallel question that I'll briefly go over is, now that we know how humans want to teach tasks, how can we design robots that can leverage that structure? And Matt talked about feedback, but feedback is only one kind of signal humans provide. And what we found was that human teaching is extremely structured, right? So we want to design robots that can exploit everything that's present in human teaching. All right, so led by Preeti Ramraj, the way we did the study, and I know I'm talking robots, but I'll describe everything in simulation. And this is not because I care about simulations more. It's just challenging to uh, do real studies with robots, especially challenging with the COVID situation, right? So the way we structured this is we've developed a world that a robot might live in. It's the tabletop world built in VBots. And then the goal of the participants in this study was try to teach the robot how to build a wall using the blocks that exist on the right side of the screen, right? So, and the task was for the teachers to teach how to build a single colored wall and then how to build a multicolored wall connected via Zoom. We had over 10 participants from diverse backgrounds, and we recorded, video, audio, transcripts, and other relevant things. So here's again, um, okay, let's just skip it. So in any case, the findings that we had was right. So in this task, what we found was that people naturally broke down the complex tasks into component concepts, right? So the task was how to build a wall. The people were able to break it down to then provide the robot with examples of what is green, what might be, spatial relationships that are relevant to the task. Next to, what does left off mean, what does right off mean, and then eventually build these concepts up into a singular task structure, right? And then as they were breaking down these tasks into multiple components, they provided a variety of different information to provide you and used a variety of modalities. And what's most interesting, I think, finding of this research is that they use or expressed a variety of teaching intentions, right? So this is what we tried. So, and teaching intention is what do you want the learner to do with that information, right? So one teaching intention would be inform. So at this point, you're providing more information to the learner to exploit, you know, what's happening on the scene. But then we also found that teachers were also trying to evaluate how much the learner actually knows, right? So this came naturally from how humans teach. So once someone showed you an example of a red box, then they tried to present, a red cone and then ask the agent, like, what do you think that is, right? So they're trying to estimate the boundaries of the learner to figure out so that they can adapt flexibly adapt to what the learner needs. So we found there were other intentions like expanding. So this would be, once I taught you, one kind of a box, I might want to expand your knowledge, your concept of what a box means. Once they found out that, the learner's envisioning of the box concept was incorrect, then they would try to correct it or revise whatever the incorrections is. So what we are claiming in the paper is that people are very structured in their learning. And the way to understand that structure is that they're teaching a curriculum, right? And they naturally come up with it. We didn't provide them with any specific instruction on how to structure this curriculum, how to break down this task, what to do differently. Like they just naturally came out with it. And they organized the teaching in a set of lessons, and each lessons targeted a specific component concept. So like it could be a property that exists in the world. It could be a reference to a specific object. It could be composition of objects. So you're trying to teach the robot how to stack. It could be a relation between objects. So it's a spatial relationship. So you are trying to teach what next to might mean. Actions, method of actions, right? So we found evidence for all this kind of teaching in our data sets. And for each lesson, so you might want to so a human might construct like, okay, now I'm trying to teach the robot next to. So they will provide information that the robot can learn from, but then they will engage in like, let me try to test the robot, try to figure out what its boundary conditions are, let me try to fix it, right? So each lesson would have a variety of different intentions. And so as we think about robots that can handle the structure, we have to think about how we can first recognize what the human is intending the robot to do with this information, and then and then respond appropriately. And the reason we want to do that is because humans are incredibly adaptive and flexible, right? So the more information you can provide back on your own boundaries of learning, the humans can really adapt instruction and make it easier for the robot. The second main finding in this paper was that people are very flexible. Like I said, they react to learners' failures and successes. They have very different teaching styles. So, for example, P6 had this style which we call narrative demonstration, where they're demonstrating the task and they're like giving a commentary on what they're doing, right? And so that would motivate a different kind of a learning method than P10, who teaches with interactive examples. So they are like presenting, setting up the scene, and then they're asking us like, what can you tell about it? These are 4 blocks and things like that. And then we also realized that people brought their background assumptions into their teaching, and actually the hardest um, uh, basically the worst teacher in some ways were people who had most programming background, because they literally try to teach the robot for loops and things like that, and that's extremely unnatural. So like paying attention to people's background assumptions is useful and critical. All right, so what this study does is it sets up a desiderata for a teacher-centric interactive task learning system, right? First, we want to leverage structure that's apparent in human teaching, which means for us is we want to look at lessons that are focused on component concepts. We want to learn from a variety of different informational sources. We want to recognize teaching intentions. We want to understand what is it the human is trying to do, what kind of instruction are they providing, and then process that information appropriately, and then provide meaningful responses, right? If it's an informed lesson, then we want to tell them, have you processed the information or not? But if it's an evaluate lesson, we want to actually expose what we know and what we don't know, right? So understanding this intentions of teachers is incredibly important, and that helps the teacher really define or structure the lesson really well. All right, so moving on to the next part, once we know how the teacher structures their lessons, how can we design robots or AI systems that can process those lessons well? So this research was done in the context of this DARPA program that's still running. It's called DARPA Gala, and the main question that they're asking there is, where does meaning and language come from? Right. So the criticism is when you look at NLP like BERT, GPT, they derive meaning from statistical patterns and word usage, but robots live in physical worlds. So that kind of language processing is not super helpful to robots, right? You could think of grounded language processing. So these are relatively newer techniques. So these are tying vision and language together. So you are either trying to generate a caption that goes with the picture, or given a question and a picture, you are trying to figure out if that question can be answered with the picture. And again, like that's connecting vision and language, but again, those models are not really relevant for robots, because robots not don't need to just generate labels. They actually need to isolate and find what is, if I told you move the green sphere onto the red cube, then you need to localize green sphere onto a specific object on the scene. You want to know what onto really means, because you have to create that spatial relationship in the environment, right? So robots have this challenge of try connecting the words with concepts that exist in their physical world, right? And none of the language models really get us there. So we are trying to build systems that can make these connections, and we are trying to study what would language learning mean within this context. So we're doing this, we're building these out in cognitive architectures. And I know cognitive architectures like have a bad rep. The community has done a really bad job in explaining what those systems actually do. So here's like my understanding of, my way of describing what this is. So there is SOAR. SOAR is a AI architecture that's designed for reasoning with complex finite state machines and Markov decision processes. Right. So this would be something like if you have to have Markov decision process for action, action reasoning and dialogue reasoning. So how would you put all of those two complex MDPs together so that the architecture can reason in a joint space of that? Then, the states, you don't enumerate the state the state space completely, but it's generated on the fly based on a set of rules, right? Each state is complex. It's represented as a graph, and it's designed based on human problem solving. So, and a lot of AI techniques like planning, hierarchical task networks, rule-based policy, reinforcement learning, they all fall out of the way these computations have been designed. So SOAR is a very complex task reasoning architecture. So that is central to how we build it, how we are building out some of this research. And the other cognitive architecture that we are using is called companions. And this is an analogical reasoning and generalization system, right? So the way to think about analogical reasoning is graph matching. So you have a graph that represents the knowledge that you currently know, and you have a graph that's the current scene in the world, and what you're trying to do is, okay, how does the current scene in the world match to what I know? And you can always fill up the graph based on what you already know, right? So this is graph inference, this is link prediction. So companions is an architecture that can do this really well, and the algorithms that are designed in that system are basically validated through human studies. So there's strong evidence that this is how humans reason about the world and learn about the world. All right. So what we have done in this part of our research is that we are trying to frame what collaborative learning would look like, and then we are designing a neurocognitive AI architecture for interactive task learning. Right. So you have a trainer that is interacting with a learner through a shared environment, and the shared environment has two channels to it, right? One is the interaction channel. This is where the instructor will provide an intent and some content. The environment channel will be the scene, right? So now the instructor can set up a scene and then can say, can you verify if there is a green cylinder? The learner then processes all of this information. So there's a deep vision component that's processing the camera image that's coming out of it. Then we are abstracting away the concrete representation into more abstract ones that SOAR can reason with. It may come out with an abstract action representation, which then is implemented in the environment. And then, so that would form the inner loop of the learner. The external loop is about language processing. So you start looking at what intent was provided, what content existed, and now can I ground green to something that I'm seeing? Can I ground cylinder to something I'm seeing? And then at some point, the architecture says, okay, this is new. So green is a new concept to me. So let me try to store it in my concept memory. And concept memory is the part that's like trying to learn the representations of what a green concept would be, what a box concept, what does moving mean, things like that. So we are slowly fleshing out this architecture. We are super excited about it because cognitive architectures used to live in this symbolic clean worlds, and now we are pushing their boundaries, and we are trying to integrate deep learning architectures into it so that we can get to a fully embodied cognitive architecture. All right, so let's see if this what all right, so this is playing. um that goes away. All right, so it's a quick sort of demonstration of how this works. The instructor can start with saying, hey, can you verify with this a cone? The agent comes back and says, oh, I don't know what that is. So that's failure, that represents it. And then the instructor can start presenting it with more examples saying, oh, that's a green cone. And so this is very similar to what we observed in our human participant teaching, that they react to what the agent knows and doesn't know. Right? And then as this experience progresses, you'll find that the agent is able to learn representations that it can combine later, right? So it might learn green in one context, it might learn on top of in a different context, move in a different context, and then when I ask like move a green box to the top of the red cylinder, it can combine these different um, concept representations together to actually do the task, right? So that's where we're at with that. And so I wanted to spend a little bit of time talking about the challenge of evaluating interactive hybrid AI systems, right? So it's always a challenge to evaluate these interactive systems. So we are drawing some inspiration on online learning methods. So we created an interactive concept learning benchmark. The agent is supposed to learn visual words, spatial words, and actions. Um, and the way we are measuring if it's learning in an interactive way is, first thing we're trying to measure is the learning active. So this is number of examples the agent extracts from its training. Then we want to learn how quick. So we give it a generality exam, right? So after we give it one informed lesson, right? is supposed to teach it about the concept. We then try to verify how much it can apply this current uh, con- concept knowledge to different contexts. So we'll give it verified tests. So we will do something like, we taught it green cone, we placed the green cone amongst other distractor objects and tried to ask, like, can you verify if there's a green cone? And then we also want to, one of the main challenges of interactive learning systems is that they tend to be overgeneral. They tend to overextend their concept information. So we are trying to, we measure that through a specificity exam. So we would provide some negative tests. So we would say, hey, can you in this test, in this setup, verify if there's a yellow box or not? So the answer should be no, right? So this is how a trial is sequenced. There's a sequence of first an informed lesson, then the agent is given a generality exam, and then there's a specific exam, and then there's another informed lesson, right? So it gives a sense of like you're learning as you are being tested, as you are being, using that knowledge to reason about your world. And what we found is like the
Shiwali,
agent that we had, yes.
1 more minute to wrap up.
Yes, I'm almost done. So it can learn diverse types of concepts, learns smartly and actively, learns very quickly, maintains concept boundaries. All right, can learn composite tasks too. So what we have now is this neurocognitive architecture that is doing reasoning in the concrete space, but then also can reason about abstract goals and then reason about even a higher abstraction of the world. So it can do analogical reasoning and generalization over the concepts. And I'll pause here. Thank you so much for inviting me, and I hope this was interesting.